We're ready.
Okay. So pH for weak acid and base. So far we have only calculated pHs for the strong acid and strong base. Now we're going to learn today how to calculate pH for weak acid and bases. So weak acid, just to remind you from last class, strength-wise, weak acids means they don't dissociate completely into their ions. So the hydronium ion concentration isn't the molarity of the original acid. Therefore, we need a set of equations to solve. Since not all weak acids dissociate into hydronium ions, we can now bring up equilibrium from last semester, where there is a reverse direction. So, Ka, equilibrium constant for acid. What do big K means? From people who took class Chem 2 semester, what does K, the big capital K means? Yep, equilibrium. So sub A, the A in a subscript tells you it's an equilibrium of acid. Equilibrium constants are known values for weak acids and bases. So they're given values. Whenever you see Ka, they're weak acids. So since Ka is an equilibrium constant for acid, what could be a symbol for base, equilibrium of base?
KB.
Yep, Kb, K with a subscript of B, lowercase b. So we're going to look at this hydrofluoric acid today and kind of see how it works to calculate pH of it. Hydrofluoric acid, if I rewrite this on my board, also I could simply rewrite this into can we also see this? Not including my water part, because there's a reason why. And by showing a double arrow, it tells you that my conjugate acid is going to donate conjugate base, reforming my reactants, original reactants. Other way, because the one that how I wrote it tells you, because equilibrium is a concentration of products over a concentration of reactants. In other words, Ka is equal to parts that dissociate and over a part that doesn't undissociate, that remains it. But they should be equal. They're arriving to an equal point at some point as the reaction goes on. So, if I plug into this number, then it's a concentration of chlorine ion, which is one of my products, and concentration of hydronium ion, which is another product, over a reactant, concentration of hydrofluoric acid. One thing to notice, there is no water concentration. That's why I have written in a simpler form where there is no water forms. We could ignore water, because water is a liquid, pure liquid or solid, they don't change their concentration, whether they have activity considered as a 1. So we could ignore water concentration in our weak acid and weak base pH calculation. So since it's an equilibrium problem, back to remember in Chem 2, where you use ice table, initial, change, and equilibrium. And moving on to, what if I start with 0.25 molarity of HF? I'm going to start with my hydrofluoric acid with 0.25 molarity. And that is my initial value. Calling it ice table. Since we're starting with the hydrofluoric acid, we didn't have anything forming as a product at the starting point. So there's a 0. We have none of any of the product yet formed. And the next table is the change. Since we don't know how much it changed, we can make it into a variable. Since some of the hydrofluoric acid starting with a 0.25 molarity, it's going to lose some part, making into hydronium ions. So if I make into an X variable, losing X amount of it from starting point of 0.25 molarity. But I'm making products, so I'm adding X much that I lose X in my initial part. And as they reaches equilibrium, I can make this into 2.5 minus X will be my hydrofluoric acid at equilibrium, losing some part of it to make it into a product. And I will have hydronium ion as an X, because 0 plus X is just X amount. I'm making just X amount of the X amount that I loses, and also for fluorine ion, I can make X amount. So if, yes, Danielle.
So, like for the C part, how do you know what you're going to be subtracting?
How do I know? If I start with something with the reactant side, but nothing given with the product side, then there's nothing to make product side to push this arrow back to reverse reactant to form hydrofluoric acid. But we have starting amount with hydrofluoric acid, but none with the products. That's the only way that hydrofluoric is going to lose some part to make a product. Does that make sense? Is that what you're asking?
Kind of.
Kind of. Or else, if there is a different coefficient in front of it, that changes the differences. Because if I had a 1 hydrofluoric acid makes 2 hydronium ions, now it changes into, since whatever I lose 1 of the hydrofluoric acid, I'm going to make 2 of hydronium ion. That's when I have to put 2 in front of 2x in front of it.
Okay, but like how do you know what the X number is going to be?
Now that's where we're going to solve it for it.
Oh.
That's why there's a K. So equilibrium constant, equilibrium, when they reach equilibrium, they have this equilibrium constant called K. So that's where we bring Ka, where constant, equilibrium constant of acid, where this amount is going to equal to this amount, where some of the part that we're going to lose in a product reactant sides will going to equal to the part that is dissociating to it. So that's how when we recall a K equilibrium is equal to the concentration of product over concentration of reactant. Which we could a reaction over there saying that equilibrium constant of acid will be equal to part that it will be dissociated into hydronium ions and then fluorine ions. So the part that it won't dissociate will be on the reactant side. Concentration of hydrofluoric acid. So now since Ka is always given number, we could solve for x's. Because it's all the same variable, we could solve it for it. So Ka, now we set up an ice table, that's the first thing to do it. Shows it starts with the 0.25 molarity and with none with the product side. Now, we're changing some amount of it that will make into product. And it reaches an equilibrium where on a part that dissociates into it will equal to part that undissociated. And then now we can use these values to solve x's using Ka equation. Since Ka is always given on your problems, which in this case, equilibrium constant for hydrofluoric acid will be 7.1 to the 10 to the negative 4th power. So instead of putting Ka, now I could plug in numbers from my ice table and then the given constant equilibrium of acid. So my KHF will be 7.1 times 10 to the negative 4 will equal to the concentration of hydronium ions, H plus, will be X, and concentration of fluorine ions times concentration of fluorine ions will be X. Now, concentration of my hydrofluoric acid will be 0.25 minus X. Now, if I simplify this simply with X times X will be the power, second power, X to the second power. Then I'm going to simplify more by getting rid of my division part into one single line by multiplying 0.25 minus x in a both side away. Then my equation will be x to the second power, 7.1, 10 to the negative 4, times 0.25 minus x. And always we want to put everything variable into one side, making it to a 0, and on the other side, I'm going to put 0 before that. Let's do more math. So for the distribution, we're going to make this into a larger form by multiplying each constant with a variable. So that would give you, sorry, 0.775 times 10 to the negative 4 minus 7.1 times 10 to the negative 4 x equals to x to the second power. Now, as I said before, we're going to move all the variable into one side, make it equal to 0. So, because I want to keep my x to the second power, a positive number, I'm going to move everything onto my, this is my left side. So 0 equals, if I add 7.1 to the 10 to the 4th power, negative 4th power x, so on both sides, then I would have plus 7.1 times 10 to the negative 4 x. And then now I'm going to subtract Can you see? Is it hard to see? So, now, looking at this equation, what could we use to figure it out?
Quadratic equation.
Yes, quadratic formula. So, we're gonna solve it for x using quadratic formula. And anybody remember quadratic formula to solve for x? Sort of.
It's opposite b plus or minus square root b squared minus 4ac all over 2a. It's a solved.
So, we have this quadratic formula to solve it, and we're going to use quadratic equation will be ax, because this matches up with the quadratic equation having ax squared, x squared, a being 1, and then bx. Plus bx, b is going to be this constant, with bx plus c equals to 0. So now we're going to apply this into a quadratic equation, solve for x, which Elena just had said, minus b plus or minus square root of b squared minus 4ac over 2a. And if we do that, solve it for it, it will be, I'm using this equation to solve for x. So now I'm going to put my variables, all my variables into this equation. So it'll be minus, my b will be 7.1 times 10 to the negative 4. So 7.1 times 10 to the negative 4 plus or minus square root of b squared, the same number, but without a negative sign in front of it, minus 4. A would be a number in front of it which is emitted as a 1. So it's 1 times c, which will be my last number, negative 1 point. Negative 1.755 times 10 to the negative 4. All over 2a, which is 1 in front of x squared. Same time, I'm just going to give you an answer. There will be two answers because one is adding, one is subtracting. So there would be a 0.013 or a negative 0.018 would be that answer. So now we have to sort of figure out which number would make sense. Any ideas? 0.013? Why would this work?
Because you can't have a negative polarity.
Yes, so because having subtracting a negative to negative, that's not, can't have a negative concentration in our real life. So we're always thinking the positive one. So if we say this, now x is a 0.013, that gives me a concentration of hydronium ion. Now, we're not done. We just figured out concentration of hydronium ion. So there's one more step to go. So the last step, we're using, now they're asking for pH. Now we have to plug in numbers for pH formula. pH is equal to negative log of hydronium ion, which is also a negative log of H plus simpler form of it. pH equation is same for strong or weak. So since we know H plus or hydronium ions has a concentration of 0.013, we're just going to plug in numbers. Solve for it. It gives you any questions on calculation for pH using quadratic forms and ice table. Yes, Elaine.
So if we had a different acid, would you take the concentration of the positive ion?
Yes, because is there a negative concentration? No, because in reality it doesn't make sense, so we always take the positive one.
But in the equation, you would, to plug into the log equation, you would take the positive?
Yes,
ion?
yes. Yes,
If you were doing dilution math like what we just did, would you use the 0.013 as the concentration of the acid?
dilution math as a 0.013, and this
Yeah.
concentration as a dilution math. But when we use a dilution math, it only uses what we're given with, right?
So like if we solved for that before,
Yes, before, and if they're asking you how to dilute things?
like if we're using that, if we solve for the concentration of that and then we were trying to solve for the concentration of like a strong base, then would we use the 0.013 as the concentration of the acid?
Strong base, when we say strong base, we're not using anything like ice table. Am I off in your, you saw something with it?
I think what Colin is referring to is if you titrate a weak acid with a strong base, and then yes, you're correct that that's the hydronium concentration there. Now, for you guys, we are only going to do strong and strong titrations. We ask that you know the curves for weak versus strong for either of them. But that's a lot more legwork that you'd have to do instead of just M1V1 equals M2V2. Because remember, even with M1V1 equals M2V2, you still have to look at the balanced equation in the first place just to see, is it a 1-to-1 ratio, 2-to-1 ratio? But if it was a weak acid like Colin is saying here, then yeah, 0.013 is the hydronium concentration that would get balanced out by the base. Not necessarily its beginning molarity of 0.25 in that problem. But we're not going to cover that. That's not first year chemistry in college. That's second year chemistry in college.
Okay, so do we have any more questions? Or we can move on. Now we're gonna look on something with more than one hydrogen that can be donated, called biaprotic or triaprotic. But I don't think we're gonna do triaprotic right now, or even in this.
I think we have percent ionization still.
Oh, we have one more thing. Percent ionization. Also, bases use the same thing. It's just Kb instead of Ka, giving you a. And be careful if they ask you. Most time they're going to ask you pH instead of pOH. So there's one more conversion to do it using the equation. And there's a table on Ka constant and Kb constant on the following pages on the board. So percent ionization. Percent ionization is ionized acid concentration at equilibrium using what we have just calculated for X over initial acid concentration. So if they ask you for percent ionization, just using a ionized acid concentration, because that's what you have to solve for, 0.013 at equilibrium, over initial acid concentration, which is first given value to you at the problem, 0.25. And that will give you 5.2%. In the book, it mentions how kind of percent ionization helps you to do do a shortcut way of quadratic formula, what we have just went through, but we're not gonna kind of go over it today, but in the next class, we will tell you how there is a shortcut way to do omitting all this quadratic equation. Once more, textbook does mention something about taking approximation instead of using the quadratic formula, but we're gonna do this, we're gonna talk about this next class. So now, what about polyprootics on an acid or basis, like diaprotic or triaprotic? And since each steps have one protonation, so there will be always more than one equation that gives you hydronium ions. So why don't we take out a worksheet that you have just picked it up on when you're in. We're going to look at question number one. To talk about it. So why don't we take the time to read what the question is asking? Number one question. So it says, what is the pH of diaprotic acid like sulfurous acid with an initial concentration of 0.45 molarity? Equilibrium constants are 1.3 times 10 to the negative 2 and 6.3 times 10 to the negative 8. Since there is right away given with equilibrium constants, we know it is a weak acid. And it has two equilibrium constant given, and we're going to figure out how we're going to use both of this equilibrium constants. So for diaprotic, there's two protonation going on. Two protons are going to be donated to a water. So first protonation will go on as sulfurous acid, H2SO3, the water, to weak acid, so double arrow. So I'm going to make a product, so I'm going to make that into a reactants, making hydronium ion. Since now, to first protonation, one proton will be given away, so still there's HSO3 minus. You have to be in my product side. To make it into simpler form, since we're not using water concentration in our equilibrium, we can say H2SO3 will form H plus and HSO3 minus. Always the first thing, and I always like to write Ka equals 1.3 times 10 to the negative 2. So back to an ice table, always when you see an equilibrium constant, big K, you have to write an ice table to form it. So my initial is given by 0.45 molarity. And since it's starting the reaction, nothing has formed as a product, so I have a 0 to start. And for a change, we don't know how much it's gonna dissociate into hydronium ion and an ion, so I'm gonna make a variable with x. We're taking away away some of the initial concentration and making it into products. So I'm taking or losing X amount, and I'm making some X amount in the product side. And my equilibrium so will be 0.45 minus X amount forming. So now we can use Ka constant to figure out my axis. So since K equilibrium is equal to concentration of products over concentration of reactant, I could write a 1.3 times 10 to the negative 2 equals to my 2 of my product, which would be x squared over a reactant. Concentration of reactant will be 0.45 minus x. And we're going to simplify this form into, well, am I getting eliminating this? Convert this into a one line with multiplying by 0.45 minus x on both sides is going to give me 1.3 times 10 to the negative 2 minus x and x squared, and making everything on one side 0, and this will give me a x squared plus 1.3 times 10 to the negative 2x and minus 0.00585. And here's my A, here's my B, here's my C. I'm going to plug in numbers into our quadratic equation with A, B, C. And for time-wise, I'm just going to give you x will equal to, you plug in numbers, x will give you two values, one with the positive, one with the negative. We're going to take the positive one, and it gives you 0.070. Now, what we had just solved for was concentration of hydronium ion. However, there's a problem, we're not done. There's one more protonation to be happen. HSO3 minus, we're gonna make some hydronium ions. So we're taking this ion, anions, and making one more protonation. So HSO3 minus, I'm just going to right away write in a simple equation, double arrow, saying that it is a weak acid because they are given with the second equilibrium constant, making H plus sulfide ions. Since we have made 0.070 molarity, we're starting with 0.070 molarity as an initial point. Also, we have also made 0.070 molarity of hydronium ions. We're starting at 0.070 molarity for hydronium ion, but we never have made a sulfate ion. So starting with none. This is how I wrote, so I'm gonna change to what you are used to it. And my change will be, since we don't know, we're gonna make it into variable. We don't know how much is gonna be dissociated into hydronium ion and sulfate ions. We're gonna take losing X amount, gaining X amount, gaining also X amount. Since 1 to 1 to 1 ratio, gonna have change, same amount of change all across. So my equilibrium, we're going to be 0.070 minus X, 0.070 plus X, and X. Just down there.
So if you have to do like another one, do you know because there's another age?
Yes.
That's okay.
Yes, so any formula that has H3A will have 3 protonation, and it's gonna give you with 3 Ka or Kb values. So you'll know right away how many protonation there is, and also if it's a weak acid or a strong weak base. Because weak base is going to give you as Kb, and weak acid is going to give you as a Ka. And Ka for the second protonation is 6.3 times 10 to the negative 8. So now we could set up A using equilibrium, which is concentration of products over a concentration of reactant. We could set up a equilibrium which will gonna be 6.3 times 10 to the negative 8 equals to concentration of my product will be 0.070 minus X, and my product concentration of my product will be 0.070 plus X times X. Now, there's more axes, so there's 3 axes compared to, there's more axes. If you unfold this, we're gonna have more axes. So, it's more complicated, but before doing it, now we're gonna compare, take a break and compare my Ka value for second protonation and Ka value for first protonation. Can you see the power differences? -1 is from -2 and 1 is -8. It's a huge amount. -8, 10 to the negative 8 power is so small that it won't affect a constant concentration we have started with, 0.070. Because -8, I'm gonna have 0.07000 gives me some value. So will it really matters if we calculate this part? No, so we're just gonna take the first one part, making we can neglect this number. It's too, like, we're taking an approximation of it, because it's too far away from our value that it won't really matter how much it makes. It's like measuring our hair growth in a day. Does that really matter? I mean, it's so tiny that it won't matter our value, pH, after all. So when we do this, we're gonna have 0.070 over 0.070x, which we don't even have to do math because it's going to cancel out into 1, making x just Ka value equal to x. So our pH values, since if this is my X, which will be equal to even 0.070 adding to 6.3 times 10 to the negative 8 will really give me 0.0700063. So we're just going to take pH of negative log of hydronium ion with this just what we have just formed before in our first protonation. However, there might be question asking you solving for a concentration of sulfate ion rather than asking you doing a pH of hydronium, pH according to our hydronium concentration, because it's too small that it won't affect our pH after first protonation. There are a lot of ways to ask questions on weak acid and weak base. They won't just ask you get a pH of hydronium ions. They might be asking, giving you, maybe they could even give you a change in it and then find the original concentration of the acid. And there's a lot of ways to ask. So knowing what's going on will be great to know. Once you know what's going on, with more practice and more looking at more questions, then you could solve how the question will be asking you in AP or in unit test. So, is there any questions? Yes.
Why do you get rid of the X? Like, why is the number so small that it doesn't affect?
This X or this X?
Yeah, that X.
Because think about it. If I'm comparing with negative 8 and 10 to the negative second power, it's so different that my answer is going to be have 0.0700000, and then gives my value, right?
Yeah, I
But if I take pH of all this long number, it's going to have going to give me a same pH, which is, you could even try to plug in your numbers. pH will be 1.15, but you could try taking negative log of 0.070 and then try to take pH of negative log of 0.070000063. So it won't really matter your pH. And since we also consider a sig digit, it won't count as, the value is not within our sig digit. So we're ignoring the axis. However, when these numbers are so close, like -2 and -5, that could affect your pH. That's when we need to consider a bit. Is there any more questions? Since we start off by a practice problem with number 1, we could keep working on number 2 through 7. 6 questions to work on. So, if you have any questions, just let me or Mr. Rotzenberg know so we can go around and help you. And next class, we're going to do more practice, and we're going to introduce something related to this also. And you're going to do lab on weak acids and weak bases. So, Mr. Rotzenberg, is there anything that you want to bring it up?
I don't think so. Again, they do have a pre-lab next time. You're not going to have to do all this full-blown calculation in the pre-lab, but percent ionization is one of the calculations that you'll have to do in the pre-lab. So again, read over that, know what you're doing. That will be a graded lab. The web assign is like this, though. I think there's only 4 problems total, though, because as you see, it does take some time. I guess one other thing I would note is if you know how to program the quadratic formula into your calculator, it would save you time for the times that you actually do have to solve this thing. So I know there's some people who know how to do it. You can kind of just share that around. And as far as I know, this year AP Chem Test will let you use your calculator. They typically will try to create problems that use the shortcut, but if they don't, you could always just plug it in just to be safe too if you have that programmed in.
Also, I remember I kind of used a graphing way to figure out x, and rather using a quadratic formula. I could check that over and see if I can remember that, and
Just plug it in and zero.
then find the zero value, yeah, right? That works, right? That's what I thought, and then maybe.
That's what I was doing right now, so I hope it works.